Good afternoon, everybody. Shall I start?
Yes, please do. Thank you,
Yep.
sir. I'm just switching you over here. You're good to go.
Okay, thank you. The title of my talk is Determination of Pharmaceutical Authenticity in Perl. And this is data and work that I acquired back in 2011, published in European Pharmaceutical Review in 2011. But it's still highly relevant today, and it's quite a good data set, I think, to present. So the aims and objectives then are to introduce NIR spectroscopy. Those who saw the previous talk will have seen the next section already. Then to introduce multi-spectral and hyperspectral imaging microscopy, and show how near-infrared spectroscopy can be used to detect lifestyle medicines. So those are medicines that have legitimate therapeutic uses, but tend to be abused by some people for lifestyle reasons. Multi and hyperspectral imaging, what are those two analytical techniques? And then they generate data which are called multivariate images, which require analysis. So they're chemical images, and I shall quickly cover how multivariate images are analyzed using principal component analysis or partial least squares regression. And then I will give an example of multispectral imaging to examine the tablet coatings on a genuine and a counterfeit tablet, and then do a sort of wrapping up comparison of NIRS and imaging microscopy. So near-infrared spectroscopy, this looks at it's vibrational spectroscopy. It looks at the vibrations of bonds in molecules that typically contain a hydrogen atom, a light hydrogen atom bonded to either an oxygen, nitrogen, or carbon atom. The transitions go from the vibrational ground state up to the first and second overtones. These transitions are typically 1 to 3 orders of magnitude weaker than the fundamental vibrational frequencies that you get in traditional mid-infrared spectroscopy. Molecular vibrations themselves could be divided into 2 categories: stretching of bonds or the bending of bonds, so the changing of the angles in the bonds. So typically, most people, when they do NIR spectroscopy, use the second, first, and combination regions. So that's 1100 nanometers to 2500 nanometers in the electromagnetic spectrum. And the spectrometers would typically have an indium gallium arsenide detector or a lead sulfide detector. However, there are useful absorptions in the third overtone region, which spans roughly 780 nanometers to 1100 nanometers. That region, silicon detectors, which we have in ordinary cameras, are sensitive to light in the third overtone region. So this opens up the possibility of using a low-cost camera to do potentially do some sort of chemical imaging, multispectral or hyperspectral imaging. And there have been some useful applications in the literature using silicon detectors. One of the advantages, of course, is, as I've just said, that these are cheap and widely available. So this slide here shows the NIR region from the third overtone region all the way up to the end of the combination band region. In red here, we've got the third overtone region, which is the region covered by a silicon detector. And you can see there are lots of different bonds that are sort of active in this region. So potentially we could pick up lots of useful absorptions for authenticating medicines. The instrumentation and method. I've used a multispectral imaging camera that typically is only available to forensic scientists. It was the Fujifilm FinePix IS Pro, and there was a special end-user license agreement to be able to purchase this. It wasn't available to the general public. It has the hot mirror filter removed, and therefore is sensitive to NIR radiation in that third overtone region. Attached to this camera, I had a special lens, also a sapphire glass lens, which is an industrial grade lens manufactured by Optec. So it's the SWIR OB50 with an f2 maximum aperture, I think. The extension bellows, and I used the Nikon extension bellows to convert this lens into a macro imaging lens, essentially to zoom in on say a tablet. And images were acquired using a series of bandpass filters. So these were placed between the sample and the lens, and they only permit light of a narrow, particular narrow band through. So images can be acquired at different wave bands between 715 nanometers and 1096 nanometers. In total, I used a total of 14 filters. So this is a picture of what the camera looks like. It was mounted vertically on a copy stand. A filter would be placed between the irradiated sample here. So these are the light sources, and light passes through the filter. Only a particular narrow band strikes the detector. This is the photo of the actual lens that I used. So an application then for authenticating a lifestyle medicine by near-infrared spectroscopy. So here we have two images of what appear to be Viagra 100 milligram tablet. But on the left, this is actually a counterfeit version. And you can see the debossing here of the actual manufacturer's name is actually deeper and sharper. The edges are sharper and it's deeper, so it's harder to tell. It's harder to tell this one apart. If you didn't have a genuine tablet next to it to compare it to, this would really be very difficult to distinguish by eye. This, of course, is where chemical imaging comes in. Got two boxes here. This is a genuine Viagra 100 milligram packet. This is a counterfeit one. And here we have the blister strip, I believe, of the genuine product with tablets inside. So the analysis that I've done has been on tablets that have been removed from the blister with light shone on them. It is possible to analyze the packaging as well. If you wish to authenticate medicines, you can use infrared spectroscopy, things like attenuated reflectance, ATR infrared spectroscopy can be used to determine the polymer on the actual cardboard packaging, or the actual polymer used for the blister strip, and that can be useful if you wish to authenticate medicines just from the packaging alone. Looking at spectroscopy then of the actual tablets, here is a spectrum of an authentic 100 milligram Viagra tablet removed from its packaging, and the absorbance spectrum has been converted to what's called the second derivative of absorbance. That is to resolve absorption peaks which tend to be overlapped and make them nice and sharp. And with this type of spectrum, then the absorption peak positions can be accurately measured, and they're displayed here. With a counterfeit tablet that I showed you, the second derivative of absorbance spectrum is slightly different. There are some extra absorption peaks which are not present in the genuine product. So this peak here at 7,187.5 wave numbers, and the one at 4,318.18 wave numbers. But these peaks do not occur in the genuine product, and they relate to a pharmaceutical, what's called a pharmaceutical excipient called talc, which has been used in the coating by the counterfeiter. It wasn't a particularly good choice to use, because talc is incorporated in the United States Pharmacopoeia wavelength calibration standard called Calibrator RS, and that includes rare earth oxides, erbium, holmium, and dysprosium oxide. But it also includes talc, because talc has these exceedingly sharp, well-defined absorption peaks. So a very poor choice of excipient there by the counterfeiter. Doing some sort of maths and pattern recognition on spectra, acquired by our spectroscopy of genuine and counterfeit Viagra tablets. We can do what's called principal component analysis, PCA, and project those big spectra, which have about 500 different data points in them, project them down into this low dimensional pattern space that has just 3 dimensions, and draw probability, ISO probability ellipses around the projected spectra, which are called the scores. And you can see here the circles represent projected spectra of genuine Viagra, and they fall nicely inside this ellipsoid. And down here to the lower right, you can see the crosses represent where the spectra of counterfeit versions have actually projected. So they fall well outside this ellipsoid, and therefore it's easy to reject them as class members and say that they don't belong to the class and they are likely to be counterfeit. One of the drawbacks, though, of doing just spectroscopy is it only classifies the product as being authentic or not. Where there is more than one anomalous, unusual peak, it isn't necessary. It's not easy to say how many extra components, how many extra ingredients might be present in a potentially counterfeit version. But this is where spectral imaging comes in, and it's quite handy, because this offers the potential, by giving us spatial information, there's the potential to actually determine the number of additional components. So hyper and multispectral imaging. The difference between these two names is multispectral really covers a lower number of wavelengths or wave bands, say up to 20, whereas hyperspectral imaging, you'd be looking at over 20 wavelengths being imaged, up to several hundred. Because hyperspectral imaging it acquires much more data. Typically, it's a more expensive setup. So you may be looking at £150,000 UK pounds, or a couple of $100,000 US dollars maybe, to get a hyperspectral imaging system. But a multispectral NIR system using a silicon-based detector could potentially be purchased for around about, say, £10,000. The actual data itself, once it's acquired, is called a multivariate image, and the analysis of this 3-dimensional data cube, which has spatial dimensions X and Y, but also wavelength dimensions, it is called multivariate image analysis. The traditional way of analyzing these 3-dimensional data cubes is an interactive approach that involves drawing polygons, regions of interest masks around scores, and flipping between the score space and the original image scene space. So it's called image segmentation. And it's achieved by selecting clusters of pixels from a principal component scores map, which involves scaling the scores generally to being in a sort of 8-bit space. So the scores are scaled to have values between 1 and 256, and the map then allows scores to overlap, and we can use we can produce bins of the number of scores that overlap in a particular combination of principal component scores, and use color maps to show pixel density, which could be useful for then drawing a polygon around a region of spectral scores, and then flipping back into selecting those scores, identifying where they're based in the original image scene, and producing a false color image to identify the spatial locations. So a schematic here of a multivariate image. We have X and Y pixel dimensions, and also a wavelength dimension here, which represents the image acquired at each of the different wave bands. It's possible to look at it another way and consider it a multivariate image as a set of spatially resolved spectra. So each pixel then essentially, or is a voxel, it's a spectrum. So what multivariate image analysis does is it takes the three-dimensional image cube, converts it into a principal component scores map, and the scores clusters show pixel density. So they've got a color-coded that uses a color map that shows regions of high pixel density, which is useful for then drawing around polygons and then converting back into this original image space and giving the pixels individual colors that allow the sort of spatial the spatial arrangements of ingredients to be determined. So multivariate image analysis requires principal component analysis. So the data cube here, which would be the spectra X, which in this case has 320 by 256 pixels and P wavelength, is unfolded by slicing it here along these dimensions to produce a big, long, thin matrix, which then undergoes what's called a singular value decomposition. It's a type of abstract sort of factorization of the data to give a reduced sort of dimension to the data. So to capture the main sources of variance in the data, but in a lower number of dimensions, so less than P. So we end up with here a series of scores vectors and loadings vectors. Okay, the scores vectors here are folded back into scores images. So we end up with a small set of principal component score images from the original data set. Looking at the spectrum of a Viagra 100 milligram tablet, we can see from the mean spectrum here, I could visually tell that it appears to contain a filler ingredient, an excipient called microcrystalline cellulose. Just by looking at that, this is the spectrum of microcrystalline cellulose. So the tablet obviously contains a considerable amount of microcrystalline cellulose in it. Moving on here to the scores images then from a Viagra, from a multivariate image of Viagra 100 milligram tablet. We can see here the first, second, and third scores images, and the first image, the loadings seem to suggest maybe it's looking at the overall intensity of the light and possibly contrast on the second image here. Potentially crystalline regions that could be drug here are showing up as these bright spots, which we can see in the image. And the third component is probably picking up something to do with the fillers. And you can see very dark regions here where there's probably a lower concentration of signal coming through from this particular component, because these correspond to probably some kind of crystalline material, which is potentially either the drug or something like microcrystalline cellulose. A pixel density histogram then of a Viagra tablet core, which has these, which is scaled to be in an 8-bit space here and has overlapping, has pixel bins that overlap with overlapping pixels in which we can give apply a color map to. We can see regions of very high pixel density, and we can draw polygons around areas here, and then flip back into the original image space and see what it looks like. So in this slide here, I've drawn these region of interest masks around different clusters of pixels, and then gone back into the image space. You can see the sort of distributions of the different materials. So in this case, I think that's microcrystalline cellulose. Multi-way partial least squares regression is another way of analyzing these types of data sets, requiring images of pure materials, probably to be able to produce regression models that will give you concentration images. Okay, and this is a schematic just showing what is done to do in order to do partial least squares regression for multivariate images. So again, it's a lot of unfolding of three-dimensional data cubes and of both the spectra and the concentrations. So sort of the Y would represent dummy variables with ones and zeros in order to produce this type of model. So that it's a type of what might be called PLS, discriminant analysis, PLSDA. So here's an application then of NIR multispectral imaging using a silicon-based detector to image coated tablets. And this image shows a counterfeit and an authentic Viagra tablet. Scores image. You can see the authentic one looks darker. So there's in general, there's an overall quite a big difference already just looking at these two in terms of the intensity of the scores. Flipping into the taking the scores maps and going into the scores space with a pixel density map, we can see here 1, 2, 3, 2, 3, 4. There's at least five clusters here which represent pixels for 5 different components that are in the that are ingredients of the coating for the genuine product. But when we include the image of the counterfeit version, there's now an additional 3 scores clusters appear. So there's 3 extra ingredients, 3 additional ingredients probably in the coating of the counterfeit tablet. And if you think back to the spectrum that I showed of the counterfeit Viagra tablet, there were extra peaks in that tablet, but it wasn't possible to know just from a single spectrum how many additional ingredients might be present. And the advantage here then with imaging is that it's possible to potentially tease out that information. So here I've drawn 8 different region of interest polygon masks around the different scores clusters, and then used false color images to show the different ingredients and the spatial distributions of them in the original image scene. So we've got I think the authentic and the counterfeit, or it could be the other way around, tablets here. So you can see that basically they are, the coatings are different, and so obviously one of the products is not genuine. So multivariate image segmentation then reveals 5 scores clusters for the genuine product. That corresponded correctly with the total number of components that are actually in the tablet coating. But image segmentation of the counterfeit Viagra version revealed an additional 3 components in the coating, and therefore multivariate imaging is capable of identifying the number of additional components present. And it's not necessarily possible to do that with just traditional spectroscopy, so it's quite useful. I would say multispectral imaging and hyperspectral imaging are useful tools then for analysis of lifestyle medicines. It's possible to identify the number of components in the medicines, probably the tablet cores as well as the coatings, via image segmentation of pixel density score histograms. And that can give more information than just traditional NIR spectroscopy, so the total number of components. Images may be treated in the traditional manner, e.g. via averaging responses in pixels to provide valuable spectroscopic information. And with both multivariate image analysis and regression, the results can be visualized as images, and this saves having to look at large tables of data. So that also is something that's quite appealing. So we can visualize the results rather than just have to stare at tables of data. Thank you very much.
There we go. Thank you very much to Dr. O'Neill. Let's go ahead and give him a round of applause. Dr. Andrew J. O'Neill coming to us from across the pond, way over there in lovely, snowy, fireplacey England.